What I want to go through today is the last main topic called radiation exchange between gray surfaces. This topic, we're taking what we've done so far with our black body radiation exchange, where we've been assuming is captured by sigma t to the fourth, or something called the emissive black body power, or E sub b. We're taking that and we're now extending that ideal model to a real surfaces. But there's maybe one caveat there, and that it's not entirely real surfaces. These are gray surfaces. So these are surfaces where the emissivity is not functionally dependent on the wavelength, but it's not one, right? It's not a perfect emitter. That's something less than that. So we'll go through some principles that you need for the homework to be able to do that with this in this area. And then hopefully there's time for a quick example at the end. All right, so the idea behind a diffuse gray surface radiation exchange is sort of the following. So let's go back to this three-surface model that we talked about, I think, a couple times ago or last time. And what we did for this model is we break it up into three surfaces with each represented by a node. Right, so we can do this, like I said, because we assume the temperature is isothermal across all the entire surface. So regardless of where you are, it's isothermal. Is that real? Like, is that really what would happen? Not really, because as you get closer to the corners, things will change and so on. But for our assumptions, let's just assume it's isothermal. And in each of these nodes, there's maybe some things that we can model or consider. So before we said, let's say we have some heat transfer Q dot across this node 1. And let's assume that this surface here has emissivity. So this surface 1 is a black surface. Let's assume surface 3 here, this emissivity 3 is equal to 1 as well. So we have two black surfaces. What's maybe different about this problem is let's look at the properties over here of node 2. So let's say that this is emissivity 2 is not equal to 1. Let's just say it's equal to something else, say 0.1. Let's furthermore assume that there's no transmissivity, right? So light is not transmitted through, it's either absorbed or reflected. Let's say that this is a diffuse gray surface, so absorptivity is equal to 0.1 as well, right? Because absorptivity equals emissivity. And then that leaves the reflectivity, rho 2, to be whatever is not absorbed, right? So that's going to be, in this case, 0.9. So now we have this second surface that's doing some kind of interesting things. So what happens if we kind of trace through the process of radiation exchange between these surfaces? So first we would start off and maybe looking at surface 1. So surface 1 is going to be it's emitting diffuse radiation. Some of that radiation goes free. The radiation that goes to surface 2, what happens to that radiation? Well, in a black body model, all of that radiation is absorbed, and then it's re-emitted at the temperature of surface 2. But in this case, now we have reflectivity. Like we have some significant amount of the light that's hitting surface 2, 90% of it, in fact, that's not absorbed at all. It's just reflected back. So from surface 1, now you have this reflection, and the reflection is diffuse, right? But that is in proportion to that reflectivity value. So you start seeing that like you have radiation from 1 to 2 and 2 to 3, and like all of those things, so you can either have a direct path from 1 to 3, or you can have this kind of indirect path from 1 to 2 to 3. So by the time you consider maybe what's happening just here at node 3, we have to account for the light that's coming in, or the radiation that's coming in, to be coming in either directly from 1 or from other surfaces indirectly from 1, right? And that's in addition to like what's being emitted from surface 2 in the first place, right? So you start going through this and you realize, okay, I've got emission, I've got reflection, and I've got all these surfaces interacting with each other. how am I going to develop a set of equations that now lets me solve for the temperatures of the system, how much total energy is coming into each node, and so on. So what we're going to do is we're going to introduce this idea of something called radiosity, and radiosity is a measure of the total light that's coming in. So to get to that point, let me just give you some definitions here. So let's take a surface down here. Come on, take a surface down here, and then consider what's happening. So let's say we have some light coming in. So we'll draw two rays coming in. Some of that is absorbed, so it's absorbed here, and then some of that's reflected. And then from the surface, we actually have stuff that's emitted as well. So let me just label some of this. This stuff over here that's coming in, we'll call this incident radiation. It's also called irradiation. Irradiation, and we give that the symbol G. All right, so G1 would be the irradiation coming into surface 1. Then there's this reflected component. So this stuff here, right, this is, oops, sorry. Draw it this way. This is reflected. The stuff that's leaving, this total stuff here, right, this, I'll draw this bracket again. This stuff leaving is a combination of what's being emitted and what's being reflected. Right, so this over here was emitted. So the combination of those two things is called radiosity. So this is radiosity, and we give this the symbol J. All right, radiosity J. So what we're going to do is we're going to develop models in terms of radiosity and in terms of black body spectral power, and we'll see how those two things relate to each other. Some notes that I want to make here. So let's say we have, let's see, at a given temperature, we have some surface, and that surface is emitting power, so it's E that's being emitted. So the power that's being emitted is equal to EB, the black body power, times the emissive power, or sorry, the emissivity, epsilon. So this is really just the same thing as saying epsilon sigma T to the fourth. All right. So at a given temperature, the power that's being emitted is related to this equation. What do we know about if we have, let's say, an emissivity that's less than 1, what is that saying about how much a real surface emits relative to the black body? It's saying it emits less, right? Like emissivity less than 1 multiplied by sigma T to the fourth, which is our black body power, is less than the black body power. So at a given temperature, a real surface emits less than a black body. Okay, so if we tried to go through and develop a set of equations using our original black body exchange, where we're just black body emissive power, and set up a system of equations that way, that model actually breaks down. Like it's not valid. So we'll just say here that the black body emissive model breaks down. Right? And why is that? Like, why does it break down? Well, because what we're trying to do in a black body model is somehow relate like the emissive power, this potential that's between two nodes in terms of EB, right? We go through and we develop it in terms of EB. But EB is ultimately dependent on temperature. So if now we're like multiplying our black body power by this emissivity epsilon, times sigma T to the fourth, right? That is saying now, in order to get the same energy exchange, I have to have a higher temperature, right? My temperature, the surface temperature has to be higher to achieve the same power out of that surface given that lower emissivity. So the whole model that we set up kind of breaks down. So we need to modify it in some way to account for this emissivity entering the equation. All right. Another note that I just want to make here, there's some ideas around irradiation. So irradiation, this is basically radiation from all sources. So all sources, let's say j, lowercase j, equals 1 to n, hitting surface I. Let's see. And then the other thing is that radiation from j to I can be emitted from j or reflected from j.